In this part we're going to simulate a cylinder in a box. As you can see here, we have a box with an inlet and an outlet, and in the center there's a cylinder. And what we're going to do is we're going to simulate the flow around the cylinder, and our goal is to simulate a Kármán vertex street. This is a vertex street which occurs for Reynolds numbers between 180 and 200. So to get started, we're just going to copy the right tutorial. It will be a transient, incompressible, and laminar simulation. So we're going to use the piezofoam solver. Let's look for it in our tutorials folder of OpenFOAM. Tutorials, incompressible, piezofoam, Reynolds average, Navier-Stokes. Let's copy the cavity tutorial. So I'm going to copy it to the desktop and rename it. Okay, let's have a look at the files. First of all, the 0 folder, it will be a laminar simulation. So delete the epsilon file, the K file, Ut, it's not needed. This is the turbulent viscosity. Okay, let's delete those files. Delete the R file, it's not needed. In the constant folder, delete the mesh, because we're going to create our own mesh this time with a Gmesh. It will be a unstructured triangular mesh. So delete this one. We won't be using block mesh this time. So let's have a look at the files. Reynolds average properties. Choose the model as laminar. Turbulence will be off. Save this one. Transfer properties. Let's edit our new. We're going to use 5.55 and exponential -4 square meters per second for the viscosity. So save this file. Let's have a look at turbulence properties. Simulation type res model. This is correct. So leave it as it is. Now we're going to create the mesh with Gmesh. So let's close our files and open up your application Gmesh. Gmesh mesh generator. Let's create a new file. Let's save it to our desktop. So the name will be cylinder.geo. Okay, so the file was created here. And now we're going to start with creating the points. So we click elementary entities, add new point. Just close this window and create the points with the key E on your keyboard. So now we have a geometry consisting 4 points. So let's connect the points with straight lines. So click on geometry, elementary entities, add new straight line. Just click on the point, click on the next point. Now they're connected. So now we have our box ready. Let's check the exact coordinates in the text file which was created. So you open up the cylinder.geo, and what we can see here is that 4 points were created and 4 lines. Let's change the points a little bit. But first of all, let me create two constants, which will be CL1, and it equals 0.04, and CL2, it equals 0.005. Those are two characteristic lengths which we're going to use for refining the mesh. So let's change the first coordinate for point 1, 0, 0, 0. And for the refinement, we're going to choose our characteristic length 1. So just type in CL1. The second point will be 3, 0 for the Y component and 0 for Z. The third point will be 3, 1.5 and 0 and 0, 1.50, and change the characteristic length for all the points. So it looks like this. Just save the file and reload it right here. Now this is our new geometry. Next thing we're going to do is to create the cylinder in the center of the geometry. So use the text line, and let's just create 5 new points actually. The first one will be the center for our cylinder, and the other 4 ones are used for creating the circle. So let's create a point 5, which will have the coordinate position X and position Y, and the refinement will be CL2. Now we need to define the position X and position Y for our cylinder. So position X will be 1.1 and position Y will be 0.75. Alright, and we also need to specify a radius for our circle, and it will be 0.1. Okay, so point 5 was created, and now let's create another 4 points. 1, 2, 3, 4. Let's change the names, so point 6, point 7, point 8, and point 9. Position X will have the just add the radius, so we will vary the center point. This will have plus R, minus R, and minus R. Okay, save the file and reload it here. Let's check it. Alright, so some kind of circle was created here. We click on elementary entities, add new, and then you choose circle arc. Select the start point here, select the center point like this, and the end point like this, and a circle arc was created. Now let's fulfill the circle. Check the first point again, start point, center point, end point, start point, center point, end point, start point, center point, and end point. Okay, now we have a circle. Let's reload our file here. So the circle was created, and what we're going to do next is we're going to create a plane surface, which we're going to extrude. So I already saved it. Let's reload it here. Now you click elementary entities, add new plane surface, click the surface, click a hole boundary, and then we press E to finalize our selection, and now we have a new surface. So the next thing is we need to extrude the surface. So click on geometry, elementary entities, extrude, translate, surface. And the Z component will be 0.1. Close it, click here, end the selection with E, and we have extruded our surface. Let's check out our text file now. Okay, so new line loop was created and a surface which was extruded. What you need to add is 2 lines. The first one is layers of 1. This will guarantee that we have a 2-dimensional mesh afterwards, because we just have 1 layer in the Z direction. And also recombine. This will recombine the triangles to it will make the triangular mesh into a quadrangular mesh. So let's do it like this. Now we just need to name the surfaces. So save it and reload it here. Then you choose physical groups, add, surface, and then we just click on the surfaces. So this is our first surface, we click on E. Then we go into our text editor, the surface appears, and we're going to rename it into inlet. This will be our inlet. Save it, reload the file here, and let's add all the other surfaces. Add surface. Okay, next one will be the outlet. Then top and bottom walls. Okay, now let's check front and back. Okay, let's check our file. This one was our outlet. This one was top and bottom walls. The fourth one is front and back. Front and back. Save it. Reload it. And the thing missing is our cylinder surface. So just choose physical groups, add surface, and then choose all those small surfaces like this. Now it should appear here. Okay, let's call it cylinder wall, and save the file. The next thing we need to do is to create the physical volume. So just add another line here, physical volume, call it internal equals 1, and save the file. And what we also need is a refinement behind our cylinder. So we need to create a line so that afterwards we can refine the mesh next to the line. So we're going to create 2 points here. 0.5. Let's just get this one. Let's call it 0.10. It will have the coordinates 1.1, 0.75, and 0, and the refinement will be CL2. Okay, let's create the next point. 11, and let's alternate the x value to 1.5. Okay, save it. Let's reload it right here. Okay, let's call it like this, because the points already exist. Save the file, reload it here. Okay, so the points were created. And what we need to do now is we need to connect them. So elementary entities, add new straight line. Okay, now we connected them. Let's check it out right here. I chose the wrong point, it should be 100. So we'll create a new line. And what we're going to do next is to create the actual mesh. So now we have our geometry ready. And yeah, just reload the file, enter mesh, and define size fields. The first field is a attractor. Going to define a new attractor. The edge we're going to refine is our edge 54. So type in 54. How many nodes? We want to have 100 nodes for the edge. Yeah, just apply. Reload here. So create a new attractor for the edge 55, and it will be refined into 100 nodes. Okay, let's go on and create a new threshold, and the maximum distance for the threshold will be 0.3. The minimum distance will be 0.15. The field we want to apply it to is our field 1, our attractor field we just created. The LC max, this is the characteristic length for the distant max, will be 0.01, and the LC min will be 0.01 also. Oh no, this will be 0.1. So it's like this. Stop a distant max on and set as background field. Click on apply. Let's check our text file. Okay, so the new attractor was created, the new threshold was created for refining the mesh, and it was set as the background field. So now we're ready to create our mesh. So you click on mesh, and we're going to mesh in 3D. Let's mesh the surface. Alright, so the surface was created. Everything was meshed. Let me click here. Okay, as you can see, we have our unstructured mesh out of triangles. And if we zoom in, you can see here that this area was refined so that we have a nice refinement of the boundary layer and the flow behind the cylinder. And now we are ready to set up our simulation and to configure the job. We just have to save the mesh now. So I'll click on save. Now the mesh has been saved. Now you can close Gmesh. So you're going to close it and copy the mesh into our case folder. Which is this one, lecture 3. So just copy it right in here. And now we're going to edit the control dictionary. So all delta t will be 1 millisecond. Just leave the right interval as it is. For the end time, I have to look up it. Our end time will be 10 seconds. And what we also have to do is we want to track the drag and lift coefficients over time on the cylinder. So just open a tutorial which includes the function for the force coefficients. It's under incompressible, piezo foam, large eddy simulation, and in motorbike. And here it is, force coefs. I'm just going to copy it. And here we include functions. I think it has to look like this, but I'm going to check it right here. Okay, the function name has to be force coefs. Yeah, like this, it is correct. Force coefs, like this. Okay, so what we're going to change is we need to change the patch name. Our patch name was cylinder wall. Pressure name is P. Velocity name is U. Rho is rho infinity. Log true. The density will be 1. Our lift direction will be in the Y direction. Drag will be in the X direction. Let's make this point 0. The pitch axis is our Z axis. So put it like this. The magnitude of the infinite velocity, let's just set it to 1, because we're not interested in the actual values for the drag and lift coefficients, but just how they vary over time, because we want to check the residuals, and the force coefficients will give us information about the convergence of our simulation, so we're not interested in the actual value. So just set those reference lengths and area to 1, like this. Save the file. Leave the FV schemes and FV solution as they are. The only thing we have to check now are our boundary conditions, U and P. I'm just going to copy those and explain them. So what we have here is our inlet with a fixed velocity of 1 meter per second. Our outlet will have a zero gradient boundary conditions for the velocity. Top and bottom walls have no slip, so there's no velocity on them. Front and back are empty, and our cylinder wall will also be a wall with no slip. So just save the U file. Let's check our pressure. For the pressure, as you already know, inlet has zero gradient. The outlet will have a reference pressure of 0 Pascal. Top and bottom walls are zero gradient, front and back is empty, and the cylinder wall is also zero gradient. So save this one. Close all the files. And now we are ready to run our job. To run the job, just open your command line like this. Going to change the folder. Okay, what we have here is our folder contains the mesh. We need to convert the mesh into a format that OpenFOAM can work with. So we're going to start the command gmesh to foam on our cylinder mesh. Like this, execute it. Now the mesh has been written into a OpenFOAM format. Open up the folder, open the polymesh folder, and now we need to edit the boundary conditions for the empty patches, because front and back is not a patch, but type is empty. Like this. You can leave all the others as they are. Save the file. And now we can run our job. So we put in foam job, piezo foam, because it's a transient simulation, and the output into our log file. Our simulation has completed now, and now we want to check our results. First of all, we're going to have a look at the convergence. So let's check out our residuals. Open the command line. And let's execute our command foam log on log. It might take a while. Okay, now the residuals have been extracted. So let's start GNU plot and plot our residuals. Set the Y scale to logarithmic. And those are our residuals. As you can see, they have converged, and we have a nice sinus wave for the velocity and the pressure. So probably we're going to have a look at a von Karman vertex street, because it looks really harmonic. So let's have another look at our force coefficients. Let's plot them. They are inside a folder called force coefs. So I'm a GNU plot right now, and then I'm going to use this command to plot the force coefficients. In right color you see the drag coefficient, and in green the lift coefficient, and it's a nice sine. So to check your results, we could also analyze the frequency and calculate the Struhal number to see if it matches the Struhal number of a von Karman vertex street, which is about 0.18, but we're not going to do it now. We're going to have a look at our results at the pressure and velocity field in ParaView now. Now let's have a look at the pressure and velocity distribution of our simulation in ParaView. So we're going to execute the command parafoam, and ParaView opens up. Click apply, and we're going to choose our velocity field, our interpolated velocity field, and we hit play. And yeah, first of all we see a kind of stationary trailing, but then the von Karman vortex street begins, and here you can see the alternating vortexes. And yeah, this is how you calculate the instationary von Karman vortex street in OpenFOAM. To complete this simulation, I'm going to show you the P distribution, the pressure. It looks like this. That's already the end. So from the beginning. First of all, it's symmetric, but then some instabilities occur and you get your vortex street.